Okay, students, let's start our discussion now. Today we'll study about aldol condensation reactions. Well, aldol by name, you should be able to, you must be familiar with the term that it is aldehyde or a ketone which is connected with alcohol. So it's like beta hydroxy aldehyde or keto formation. For example, if you check out, this is a keto form, right? So in case if you have an OH here, what do we say? This is alpha hydroxy, right? So but if it is at the beta position, this is the beta position. So this beta hydroxy ketone is what we call it as aldol, or the other term is also used as kedol. Okay, but most of the time it is aldol which is used. Now, if you see this one also, this is also a keto form, and this position is alpha, this position is beta. So here also if you have OH, this is also a beta hydroxy keto form. Similarly, if you have beta hydroxy aldehyde form, so this is the position of beta. So these are all aldols or ketols, but most, as I said, generic term which we use is always aldol for both aldehydes as well as for ketones. See, when it comes to aldehydes and ketones reactions, these aldol formations can happen either by both aldehydes, right? Two aldehydes reacting with each other, or it can happen with a ketone and an aldehyde combination, or it can happen with an aldehyde, right? Ketone plus keto combination. So either ways, you will see an aldol can be formed. Okay. Now, once you have an aldol formation, right? So, I mean, this aldol formation which is done as you add either a ketone and aldehyde, aldehyde or an aldehyde, ketone or ketone, in the presence of both OH minus or H plus, which means both acidic medium or a basic medium, we will get aldol. So, aldol formation is observed in both acidic and basic medium. Okay. During the aldol formation, what are the important fundamentals we will be looking at? During aldol formation, we will see through tautomerization, we will see how an enol or an enolate is formed, we will see how a nucleophilic addition will happen on C double bond O, and finally how an aldol formation is observed. Okay, so these are the basic tools which are going to be seen during the aldol formation. Now, what are the most basic steps which are involved in aldol? Let us see that. Suppose if you have an aldehyde, okay, and I treated that with basic in base, that is dilute KOH. Now this dilute KOH, which is OH minus, will extract a proton from CH3 here, and it will become CH2 minus. Now this CH2 minus is in resonance stabilization with this C double bond O, and this formation is called as enolate ion, or this intermediate is what we call it as enolate ion. From this enolate ion, right, we will see this CH2 minus will attack on the second mole as a nucleophilic addition. So you can see that a nucleophilic addition is happening here, which makes this double bond to become O minus. And after that, on hydrolysis, this O minus will fetch that H plus, and we will get OH here, and this C double bond O, right. So wherever this C double bond O was, that C double bond O will retain back, and this is how we will get beta hydroxy aldehyde or ketone. Okay. So the idea is, you can see, first a tautomerism step, next an enolate formation, nucleophilic addition reaction, and finally aldol formation. So these are the four major steps which are involved during aldol. Now it could be an enolate or an enol formation, both can be observed. Once an aldol is formed, suppose if you check out this case, we have CH3, CHOH, then CH2, C double bond OH. Now once an aldol is formed, it is observed that this OH, which is at the beta position, and this alpha hydrogen, both will try to dehydrate, and we will get this as CH double bond CH double bond OH. Now the formation can be increased by increasing the temperature. So if you operate at higher temperature, it won't stay at aldol. The aldol will become this alpha beta unsaturated. This is called as alpha beta unsaturated aldehyde, aldehyde or ketone. Now this alpha beta unsaturated aldehyde or ketone is what we call it as aldol condensation. So the term, when you use aldol condensation, which means you are asking for the condensed product, that is after removal of water. Okay. So the dehydrate form of aldol is called the aldol condensation. So you can see here, when I take 2 moles of an aldehyde in the presence of either an acidic medium or a basic medium here, that would first form an aldol. That aldol after dehydration will give us an aldol condensation product, which is CH3 CH double bond CH CHO. So this is an aldol condensation product. So remember what has been asked in the question, whether it is aldol being asked or aldol condensation product has been asked. The dehydration step, the last step, which is the dehydration step or condensation step, right, is either done by E1 CB mechanism or E1 mechanism. Okay. Well, this is more debatable whether it is E1 or E2, but most of the sources have always given that it would go for E1 mechanism. I'll show you how it goes. When it comes to base, right, in case of base catalysis, if you are using a base like OH minus, once you have an aldol formation, can you see this is an aldol? Okay, this is beta hydroxy aldehyde. In the alcohol, if it is base, base will extract the proton from alpha position, right, and forms a carb anion. The reason for carb anion formation is that this C double bond O will help in resonance stabilization. And you remember that this is how the E1 CB mechanism is preferred. So it is going through E1 CB mechanism, forming a carb anion. Once the carb anion is formed, it will force the OH minus to come out so that it can form a stable alkene which can undergo resonance with C double bond O. And that's how OH minus will come out of it. And this is E1 CB mechanism. Which means when it comes to base catalyzed dehydration, always E1 CB mechanism is preferred. Okay. Now in case of acid catalyzed it is very debatable. It could go for E1, E2, E1 CB also. For example, if you check out this OH, first this OH will get protonated to form this OH2 here, and this OH2 can be removed, got it, and we will get a carbocation here. Once you get a carbocation, again OH H2O can extract the proton from here, making a double bond formation. This is a mechanism by E1. Now the same can happen through E1 CB also, where this OH2 group is leaving. Water H2O can remove this proton first, carb anion is formed, and then double bond will form and this group will leave. Okay, so which means this being the first step, this being the second step, so which means it is E1 CB mechanism. But most of the experiments suggest that this carb anion formation is not pretty much seen in acidic medium, got it. So which means even if at all I react that in D2O, right, you don't see any hydrogen exchange or deuterium exchange happening here. So which is making us understand that in most of the acid catalyzed dehydration, E1 CB is not going to occur. Rather, it will go for either E1 or it will go for E2. How does it happen in E2? E2 means these two steps are happening simultaneously. But whether it is E1 or E2, that is difficult to discuss. One case where we can pretty much say it is E1 is that if you have CHOH and this carbon, the beta carbon, if it is at the tertiary position, if it is third degree position, then we are pretty much sure that this is going to happen through E1 only. So which means first OH2 will form, this group will leave, we will get a carbocation CH3 plus, and we will have CH, H, C double bond O, H, this H is lost as H plus, and we will get this as CH3, C, CH3 double bond CH, C double bond OH. Okay, here we are pretty much sure that it is always E1. But in the case of secondary, or if it is primary, right, it could be combination of both E1 and E2, right? So you might be asked in this cases what is the mechanism. When it comes to this case, you can say that E1 is more favorable than either E1CB or E2. But we cannot say E2 is not happening, got it? But here we can definitely say it is only happening by E1 mechanism. Okay, this is again based on the experimental data only, got it? I hope you understood the dehydration step, how it is happening. In base catalyst, it is pretty much sure that it is E1CB only. But in acid catalyst, it could be a mixture of all of them, unless it is a tertiary alcohol, which will definitely go for E1 mechanism only. Okay guys, now let us see the mechanism, how the aldol formation is being done. Okay, so if you see the mechanism, first we take an aldehyde or a ketone, anything. I'll start with aldehyde first. So OH minus will first extract proton from here. This brings to the next question to us, sir, why is that OH minus is actually attacking on alpha hydrogen? Why is it undergoing addition? So this should be the first question that should come to our mind, that why can't just OH minus we get added up here, got it? Which brings to the case that we are adding very dilute OH minus. So the amount of OH minus are limited, got it? When it is limited, right, so what would happen? If you, I mean, this OH minus can do both of these cases, right? If you see, suppose first OH minus is attacking on carbonyl group, so we will have this as O minus, H and OH, right? And this would immediately close back because this double bond will become more stable and OH minus will be removed out. So you would see the reaction would be mostly on the back side. So you will hardly see OH minus attacking as a nucleophile and forming this, got it? So the other option what we have is this OH minus, instead of attacking at the carbonyl position, if it extract this proton, suppose if it extract this proton, we will get this as CH2 minus C double bond O and H, which is enolate ion. Now this enolate ion, suppose if this is the enolate ion, okay, so this enolate would be surrounded by lot of other aldehydes. So it is surrounded by a lot of other aldehydes in here, like the same aldehyde here, right? So CH2 C double bond OH minus, this has been surrounded by a lot of aldehydes around it. So then this would act like a nucleophile and have a chance to attack at carbon. Okay, so that's how the mechanism is usually expected to go. So you have to, what I said, like the enolate ion which is formed will again attack on the next moles which are close by that enolate ion, and that's how the nucleophilic attack is going to be seen. Alright, so I hope that first clarity is there, that why the attack is happening on OH minus is attacking on the alpha position. Anyone has a doubt on that? Right, check this. We will get this as CH2 minus C double bond OH. This is the first mole, which means first molecule which is forming an enolate ion. So this enolate ion will be resonance stabilized with carbon as O minus and H this way. Now this enolate ion, as we expect that it will attack on the second molecule here. As soon as it attacks, you will get this as O minus here, and the CH2 C double bond CHO will get connected, right? Sorry. And then this takes away this H plus from water. We'll get H plus from water, and we will get this as CH3 CHOH CH2 CHO. This is the second step. So first step is that OH minus extracting the proton. Second step is the nucleophilic attack. Now see the third step. Once you get this aldol form here, this OH minus can extract proton from the alpha position, and it can form CH3 CH OH CH minus and CHO, and which will close as a double bond and removes this OH minus. So we'll get this as CH3 CH double bond CH CHO. This is crotonaldehyde. If you just remember that the alpha beta unsaturated aldehyde is this crotonaldehyde. So there are three steps we have seen. First step is about enolate formation. This one is the enolate formation. Now second step is the nucleophilic addition. Nucleophilic addition will always be the RDS of the reaction. And third step, since you are taking a basic medium, that would be E1CB mechanism. Now you should always remember this. If heat is not given, you will stop the reaction at second step only, aldol only, especially if it is base catalyzed mechanism, because the amount of base you are taking is very less. Got it? But if the heat is being provided, got it? So then either with or without base, it will always come out here. Got it? So any solvent, maybe water is present there, so that will also extract the proton. Make sure it will get a double bond formation here. Got it? So there are three steps you could see which are involved: carb anion formation or the enolate ion formation, RDS, and E1CB mechanism. Out of these three steps, now all of them are equilibrium steps. So this is in equilibrium with this is in equilibrium with this, and further. Now here we have an enolate ion formation which is in equilibrium with this forward direction where aldol is forming, and in the backward direction where aldehyde is forming. Got it? So instead of taking H2O and OH minus, here the solvent we are taking, right, is H2O with a catalytic amount of OH minus. Suppose if I take the solvent as D2O and OD minus, still if there is a carb anion formation, what do we expect? That these hydrogens will get exchanged with deuterium. That is what we always expect if you have a solvent D2O, because these hydrogens will go back. You remember the tautomerism step, so it will go back, and here these hydrogens will get replaced as deuterium. But in base catalyzed mechanism, especially for aldehydes, this evidence, it has been seen that D2O failed to get the exchange happening with that CH3 group. So which means this the first step which is happening is more in the forward direction and less in the backward direction, and the second step is also more in the forward direction and less in the backward direction. Or if at all I say that rate of this backward direction K inverse, got it, and if at all I take this as forward direction K forward, so this K forward, if you compare with this K backward, this K forward is much faster as compared to that of K backward. So because of which this enolate ion is not going back, rather it is going in the forward direction to form this aldol. Okay, and this is only the case for aldehydes, remember that. So aldehydes do not show deuterium exchange. Okay, very important statement here. Okay, is this clear everyone? So the reaction here from enolate to go back is less favored as compared to the reaction going towards aldol. Okay, in case of ketones, let us see what would happen in case of ketones. Now in case of ketones, right, first same steps again. OH minus will first extract the proton, forms an enolate ion. So you can see this enolate ion is in resonance stabilization with this. Second step is that enolate ion will attack as a nucleophile here and it should form this O minus, which on hydrolysis should become aldol. Okay, so this is the aldol which we have. Now here if you see in the second step, we have bulky groups around the carbonyl position. So the attack is relatively very slow, although this is the RDS. Now if you compare the forward direction constant as compared to the backward direction constant, the backward direction constant is more favorable. So which means if at all we take the solution as D2O, then deuterium exchange can be observed. Got it? So stepwise if you observe, second step is the RDS here, right? And if you want to increase the yield and let it go more in the forward direction, try to take an anhydrous condition. So suppose instead of OH minus and H2O, instead of taking this H2O, maybe I will take some kind of a OH minus which is pure or some kind of a solid form like solid barium hydroxide. So that itself will be added to this solution of ketone and that will be serving the purpose of getting this reaction into forward direction. I hope all of you understood that. Taking water as a solvent, this reaction will be more favoring on the backward direction because this CH2 minus will again take this H plus, go back to the keto formation. Forward direction reaction is less favorable here. Why? Because of the crowding. You can see that nucleophile is also bulky and both the groups with respect to C double bond O are bulky. So attack would be very slow. Right. So check out this. Anhydrous condition would help the reaction to go forward direction or avoid the reverse direction reaction. Okay. Like I said, the equilibrium is far over to the left hand side as compared to that of right hand side. So keto formation is not observed that easily. And evidence for that is that if you add D2O, if we have solvent D2O instead of water, there is a deuterium exchange observed on CH3. Okay, right. So how do we make sure? Because the yield here is a very difficult part because this step is very slow and this is not remaining in the solution as it is going backwards. So to increase this, one condition we learned is that use anhydrous instead of water. Don't use water, use anhydrous. Second thing, the minute this is forming, right, immediately remove that off, distill it. Okay. As soon as you remove this off, reaction will keep going in the forward direction. Okay. So how can we do that? This can be done by a apparatus called as Soxlet apparatus. Okay. Now see what is Soxlet apparatus. In Soxlet apparatus, we take a ketone almost near to the boiling point. Got it? So, for example, if you take any keto form, here example we are taking is acetone. Okay, acetone's boiling point is around 56 degrees. Now, here what we are doing, this is in contact with BaOH twice in the vapor form. So, whatever the vapor forms which are coming here, they will get in contact with the BaOH twice. Okay. As they form on the surface of that BaOH twice, you can see slowly a liquid formation is observed, which is the aldol which is forming. The amount of aldol that is formed is hardly 2%. So you can imagine the amount of aldol formed due to ketone is very less. Okay, and this can be kept in liquid form as long as you have some condenser here. So here water outlet is coming, right, where it will condense this vapors and then you can remove that off. Got it? Siphoned off as in you will remove this from the solution. You can see the solution which is present, will remove that, and whatever the vapors of ketones which are present, again they will continue the interaction with barium hydroxide. Right? So the idea is you just need to know that there is a special apparatus which is used to siphon off this aldol, especially for ketones. Okay. So two things we have learned here. One, how do we increase the aldol product here, yield here? One is by taking solid barium hydroxide, which means it is a base but anhydrous. And second thing, we have to use it at high temperature so that the reaction can happen. Got it? Next, the equilibrium mixture hardly has 2%. That has to be siphoned off every time. The minute it has formed some kind of a vapors have come, it will condense and remove that, and then again some amount will form, remove that. So if we keep on siphoning off, that's how we can get those 2% ketol every time. Okay. And another thing, if we do not want to use this Soxlet apparatus, correct, we can go for acid catalysis. Acid catalysis, especially for ketones, will give you a better yield. Okay. I hope you understood the problems with the ketone, and how the acid catalysis helps is what we will see now. See, suppose if I take the same keto form here, so this is the ketone which I am taking. So 2 moles of CH3, C double bond O, CH3. So in the case of ketones, first we will see 1 mole in the presence of acid, OH minus will be the first one to extract the proton. So we will have CH3, COH with this positive charge and CH3. So I can create a positive charge on carbon, or rather delta positive charge on carbon, which means it is highly electrophilic to be reacted with a nucleophile. And second thing, if this CH3, C double bond O, CH3, in case in acidic medium, you can see it as first form OH plus here, right? And this is about the second mole I am talking about. So this H plus can be lost and an enol is formed. See the difference between base catalysis and acid catalysis. In acid catalysis, we will have a complete enol formation. In base catalysis, we will only have enolate ion. So here we have an enol formation, right? So enol formation, this is the second mole. The first mole is forming this, highly electrophilic carbon. Then the pi can attack better. So this pi can attack better on that carbon. Got it? As a nucleophile. It will attack as a nucleophile there. Correct. Once it attacks there, this carbon would get positive charge here. This carbon is the one which is getting positive charge. That will be supported by this lone pair, and it will form this keto on this side and alcohol on this side. So we will get this as an aldol. Okay. The advantage here is that we are trying to increase the C double bond OH, C double bond O, to get more and more electrophilic so that the nucleophile can attack. Second thing, there is an enol formation. That means a complete intermediate, a stable intermediate is forming. Okay, it is not a charged species. It is a completely stable intermediate form. So we can expect that it will go completely in the forward direction to form enol. The first mole, which has high electrophilic carbon, can be attacked now with the nucleophile. Okay. Now this can be enhanced, like if you want to completely avoid the back reaction, we can use dry HCl. With dry HCl, because there is no water supply here, so definitely only H plus will be used to protonate this. Got it? And this pi can attack here at a better rate. Okay. So I hope you got a basic idea that what is happening in acidic medium, right? In acidic medium, acid catalyzed mechanism, ketones will be helpful to make better reactions. RDS, irrespective of acid or a base catalyzed, is always going to be the attack of nucleophile. Okay, right. Now, like I said, under acidic conditions, earlier I told you, right, if you take tertiary alcohols, it will go for acid catalyzed dehydration and give you alpha beta unsaturated, and this will be done by E1 mechanism. Okay, so for example, here if you check out OH is there, it will extract proton from here, and we will have OH2 plus CH2 C double bond O CH3. This H2O will be removed, so we will get this as Me plus CH H C double bond O CH3. This bond is broken to make this as a double bond, so we will get this as Me double bond C CH double bond O CH3. Okay, now please remember this important point here. If it is a tertiary alcohol, right, we do not even have to provide the heat, so you will not stop the reaction at aldol, you will stop at aldol condensation product. Correct. So if it is in the case of tertiary alcohol, it will react with it will get protonated for sure, and it will form the keto form. Got it. So in questions, even if it is not given as delta, you always end up at keto form. You'll always end up at condensation form. Okay. And overall reaction is reversible anyway. So what are the formations we have seen? One is Aldol formation, right, plus dehydration. Okay. So this is what happens in acid catalysis. I guess all of you understood this. Okay, now you can start writing. Okay. Please start writing from here. See, if you see any of the aldol form, suppose if you check out any of the aldol form, you can have a double bond and OH. This is how it is, correct? So any aldol form we take, it will still have an aldehyde or a keto form on it. So if at all I bring in contact with one more mole, suppose if this is a ketone which you have, so it may so happen that this CH3 minus will attack again here. So we can see that a polymerization can also happen, right? So that is what we usually observe in the case of aldehydes. Ketones not so much, but aldehydes. So alpha beta unsaturated aldehydes which are there, they still have an aldehyde form, so which can further undergo that carb anion addition, which is nucleophilic addition, and that will keep on going till it becomes a polymer. Okay, so a low molecular weight polymer can be produced by heating these simple aldehydes with NaOH. That is what is observed. Let us see few questions based on this. Suppose if you see CH3 C double bond O CH3, simple ketone, that ketone can form mesitile oxide. Okay, in case of 3 moles of ketones, if you take the presence of dry HCl, correct, we can see this aldehyde which is formed, again that will get reacted, okay, as if it is CH3 C double bond O CH3. So this CH3 part will again react here like this, right? So and finally we will get a product, which is of 3 moles on it. So it would look like this. So we'll have double bond here with this double bond O is intact, and here, sorry, my mistake, this CH3 is attacking here. Yeah, so this CH3 is attacking here, so which means this will get involved as one more double bond here and this formation. Okay, so if alpha beta unsaturated ketones are present with acetone, it is called mesitile oxide, and if 3 moles of that alpha beta unsaturated are forming, then it is called 4-one. This is called 4-one. Now this was a question asked in 2018 that if I take 3 moles but instead of dry HCl, if I take concentrated H2SO4. In concentrated H2SO4, this 3 moles will also undergo dehydration. So imagine this as if this OH which is forming here, right? So we can have a dehydrated product this way. So it would form a complete benzene at these 3 positions, and you know that this is what we call it as mesitylene. Okay. So I would suggest you to try the mechanism. Think this way that we have CH3, you know, C double bond O, CH3, and then we have again C double bond O, we have CH3 and another mole C double bond O, CH3, CH3. Okay. So try to connect this to here, right? So this to here and this to here. And whatever the OH which is forming, it will get dehydrated, forming an alternate double bonds. Okay. So this is a hint I am giving you. So I would suggest you to try and write down the complete mechanism for it. This is how the mesitylene is formed if you take 3 moles. If you take smaller aldehydes, that may even go for more number of moles. Like if you take for example CH3 C double bond OH. Okay. So this might continue to polymerize. Got it? Next, if you see what are the types of aldols we will be learning, right? So we have self aldol, crossed aldol, Claisen-Schmidt aldol formation, intramolecular, nitro, cyno and retro aldol. These are the type of aldols we will come across. Let's see one by one. First starting with self aldol. Self aldol means we are using the similar aldehydes or keto forms, right? So if you take 2 moles of same aldehyde and react, we are expecting what should be the aldol form. See, in short, how do we, without mechanism, how we have to write, learn that carefully. Okay. First I am writing the entire molecule the way it is. You see CH3, CH2, CH up to that I am writing. This C double bond O which is there, right, that I am converting into alcohol. Okay. And from this alpha carbon, now I am making a connection of the second mole. So this entire thing is the first mole. This is the first mole now. Now I am connecting the second mole from the alpha position, which is CH, CH3 and C double bond OH. Got it? So learn the way to write here, guys. So this is the second mole now. I hope you got that. So first mole and second mole got connected this way with that carbon-carbon bond. So what we got, this is the aldol which we got. And since I am using in basic medium and heat is given, check this, heat is given, which means you have to write the final product in the condensed form. So condensed form means we will have CH3, this OH which is at the beta position and this proton which is at the alpha position will undergo dehydration to give CH3, CH2, CH double bond C, CH3 and C double bond OH. So this will be the final product. Okay. Similarly, let me take one more aldehyde here which is of this kind, right? So this is like an isopropyl which is connected to this CHO. Now if it is with KOH, what do we write? We'll write this as CH3. See the game again. I am writing the first mole now without disturbing the structure. It is the same structure I am writing, except that O which is present I am making that as OH. Second mole from this alpha position, you can see from this alpha position I am writing it as C, CH3, CH3, right, and CHO. This is what has been formed. Got it? Now at this alpha position, now there is no alpha hydrogen. Got it? So since there is no alpha hydrogen, even if the heat is given, right, alpha hydrogen is present here, so that does not undergo dehydration easily. And if you are expecting that OH minus E1CB will happen on this side, OH minus will extract from here and then double bond will form here, that is not going to give a stable alkene form. So this reaction won't happen on this side. Okay. So even if the heat is given, since there is no alpha hydrogen here, you will stop the reaction here itself. So aldol is the last product here. No condensation, no condensation product due to absence of alpha hydrogen. Okay. See the next one, how we can do that. I'll keep doing few questions so that you get familiar, and then in the assignment you can do lot of them. See, again 2 moles of this. What do we do? First, I will keep the structure the way it is. Just I'll ensure that here this first mole. Okay, now I'm writing the second mole because keto form I can just put it here itself. So keto form I'm putting here itself. From the alpha position I will make a connection to the second first molecule here, which have an OH group here, right? And again heat is being provided, so you will write the condensed form of it, so which will be double bond, and this will be the final product. Okay. So 2 moles of acetone, we have just seen how we have to write CH3 C, okay, double bond O, CH2. I am writing the second mole first because it is a keto form. Write the second mole first, which is the keto form. Then the CH2 is connected with C, which has become OH, and the other two methyl groups are present like this. Okay. So that would be the aldol form, and it will give away water because heat is been given. So we'll have this as CH3 C double bond O, CH double bond C, CH3 CH3, right? We call it as mesetyl oxide. Now if you check this, butane 2-on, especially when it comes to ketones, we can have symmetrical ketones or unsymmetrical ketones also. In case of unsymmetrical ketones, we will get two products here. So two products, what are the products which will be formed here? See, first I will write, I am directly writing the product. So think about it. 1, 2, 3, 4, 4, 5, 6, yeah. And then we have a double bond here with this, okay. Here I have made a connection with these 2 moles. Check this out. What are the moles I have used? Double bond is here, double bond is here. So this CH2 minus I try to connect here, right? When I did that, so this is that ethyl group which is present on this side, this is that methyl group which is present here, correct? And this is that CH2 which is connected here. Rest all you can see that, okay. So that's how it got connected. And finally I have written the condensed form of it. The other product which I can expect from here is this one, okay, the one which is connected from this end. You can see from this end CH2 minus which is forming, or CH2 minus, or in this case it is yeah, base only, so CH2 minus. So CH2 minus, this is connected here. So if that gets connected with this carbon C double bond O, I will get this form. Now if you were asked what is the major and minor product, you will say this is a major product and this is the minor product. Now why that is the major and minor product? Check this out. Carb anion which is formed here, this is coming with a less hindered form. This is coming from less hindered carbon trying to attack here, so which is more favored as compared to that of this carbon which is connected here, because this is coming from a more bulkier side of the carbon, right? So always prefer to the less bulkier side of the carbon here, which means kinetic enolate gives always the major product. So the enolate which is forming, right, so which is kinetically more stable here, so that would attack on that group here. So you can see that this carb anion which is at the primary position is more stable, so that would attack on this, which is the major product. It does not mean minor product is not forming. In fact, the percentage difference is very less. In fact, sorry, this is around 56 percentage. Okay, this is around 44 percentage. Got it? So, but out of this also, if major product is asked, always go with the kinetically stable enolate form. Got it? I hope you got this point, how to choose and how to make the self aldol products. Okay. Now check the cross aldol products. Cross aldol is when you have two different aldehydes or two different ketones, right? So suppose if I take these two different aldehydes, this is acetaldehyde, propanaldehyde. So if I take this, what are the products I'll get? Watch it carefully everyone. This is an area where you should be spending less time in solving and extract the answer fast. See, first I will write the self ones. Self means this itself will react with its other molecule, own molecule, to give one self aldol form. So CH3, COH, CH2 and CHO, right? Remember, first molecule, just convert this carbon into alcohol. Second molecule, CH2, alpha position CH2, connect with this. Now, similarly, if at all I write the self form for this one, self of this, what do we get? I will get this as CH3, CH, right, sorry, here I'll write CH3, CH2, CH, OH and CH, CH3 and CHO. This is the self of it. So this is self, this is self. Now during the cross, I can see this CH2 minus can attack here and this CH2 minus can attack here. So I'll again get two crossed aldol products. Right. So what are the other crossed aldol? Check it out. I'll write this as CH3, CHOH, which means I'm talking about this attack, this CH2 minus attacking on this carbon. So that, and I will get this as CH, CH3 and CHO. And next one, I'm talking about this attack now, this attack forming on this carbon. So what do we get here? We'll get CH3, CH2, CHOH with CH2 and CHO. This is what we have. Okay. Now, if you observe properly here, this is a chiral center, and here if you check out, this is a chiral center and this is a chiral center, and here also if you observe, this is a chiral center, this is a chiral center, and here this is also a chiral center, which means you have a lot of products forming actually. Correct? You will see two self products forming here, four cross products forming here. Let me write this as cross, this as cross, and this also cross, right? And here also we will see four cross products forming, and here two four self products forming here and two cross products forming here, right? So these are all the products which you will get. So you might be asked like, what are the total number of aldol products? So you should be aware to write the self as well as crossed and check out how many total products are formed. Now after this, if the dehydration happens, we will get aldol condensed product. So let me write the condensed products also. For this particular self product, I am writing the condensed product first. So we remove this OH and H from here. So I will get this as CH3, CH double bond CH, CHO. Okay. And here also you can see this could have cis and trans. So I can have two stereo products here. And similarly, if you check out this self product, if at all I write that, we'll get this as CH3, CH2, CH double bond CH, double bond C and CHO and CH3. This also has cis trans, so I'll get two more here. And here if you check out the initial cross one, this cross product which you have, I'll get this as CH3, CH double bond, C, CH3 and CHO. This is the one I have. The last one CH3, CH2, CH double bond, CH, CHO. So here also I'll have cis trans, here also I'll have cis trans. Okay. So if the question was asked like what is the total number of aldol products, you can see that 4, 4, 2 and 2, right? So total we have 12 aldol products and condensed product total 8 geometrical kind. So these 12 are optical kind and here these 8 are geometrical kind. Okay. So these are the type of questions usually asked from cross aldol. During cross aldol, it's very difficult to determine what is major product. So you will never be asked major, you will be asked total number of products in these cases. Okay. So how the products has to be formed, I hope you understood that. Okay. I want you to write from here and then I'll give few questions on cross aldol. So please write down here. On the condensed products, CH3, CH double bond CH, CHO, I have CH3, CH double bond CH, C double bond O CH3, and I have CH3, CH3 double bond CH, C double bond O CH3, I have CH3, CH3 double bond CH, CHO. So as per the chiral centers, if you see this is a chiral center, so we have 2 here. So there is no chiral center on the second one, so there is only one product. In here I have one chiral center, so 2 here, and here there are no chiral centers, so 1 here. So you can see there are 6 aldol products, and condensation wise also you can see 2 here, 2 here, 1 here and 1 here. So total 6 aldol condensation products. I hope all of you got that. Okay, so in the second slot I will take for 15 minutes to finish rest of the questions, because we have 4 more types of aldols to finish that. Okay, then you can start working on the aldehyde sheet on that. Okay, right, in the morning we discussed about crossed aldol, and these are 2 examples which we discussed. If we have only aldehydes, 2 different aldehydes, or a aldehyde and a keto form. Okay, right, like that. There was one more example, you guys can try that, where you can see it was asked about the products for these 2. There is a cyclic ketone and an aldehyde. So one, we will have a self aldol of the aldehyde here, so CH2, CHO, this is for aldehyde, and self aldol of keto form here, double bond O, and this getting attached here with OH, and one is a crossed one. Okay, so the crossed one would be double bond O, and if you check out, we can have this double bond O connected with CHOH and CH3. Okay, we can have a cross of this also. Now what happens when you have an aldehyde and ketone, right? If you were asked like what are the major products, right? So in that case, one, only aldol will be major, right? Only aldol forming from aldehydes will be major. The other one, if you check out, is this one. The cross one will be major as compared to that of keto form, correct? And within the crossed ones here, if it was asked which will be the major in the crossed ones, In the crossed ones, always the keto form will act like the nucleophile, okay, and aldehyde will always act like the electrophile part. So that would be the major product in the crossed forms. If you were asked, like, out of all the cross product, which is the major product, should always choose the one where you have aldehyde, which is been acting like an electrophile on which nucleophile is attacking, which means the keto part is attacking. In here, this keto part is attacking this aldehyde. That would be the major crossed product. Okay. Next, within this, if you have see crossed aldol happening where one of them has an alpha hydrogen with alpha hydrogen, the other one doesn't have the alpha hydrogen, okay, then definitely the one which has alpha hydrogen, that would become the donor, because the one which has alpha hydrogen can actually uh, have the carbon anion, and that is the one which will attack. So in these two also, if you see, this does not have any alpha hydrogen, which is benzaldehyde. So in benzaldehyde, you would see this form, right? So this does not have any alpha hydrogen. But here on this aldehyde, we will see it has alpha hydrogen. So this alpha hydrogen has to be removed for us with OH minus, right? And carb anion is formed, which has to be attacked on this CHO. And based on that, we would get the products, and we will have the product of this. One is pH, CH, OH, and CH2, CHO. This is the aldol which is formed. And the other aldol would be of this itself. So which means one will be crossed and one will be self. You don't see self of this forming, correct? So we will have CH3, CHOH with CH2, CHO. Now this on heating, both of them on heating will also give the condensation product, which is pH, CH double bond CH, CHO. This is the condensation product. Here CH3, CH double bond CH, CHO. Okay, I'm sure you remember this name. This is cinnamaldehyde, cinnamaldehyde, and we've been doing this already before also. Croton aldehyde, croton aldehyde. These are the products you will get. So let me revise that. Claisen-Schmidt reaction is about the aldol condensation between aldehyde or ketone with alpha hydrogen and aldehyde or ketone without alpha hydrogen. Now if at all I want to get this cinnamaldehyde to the better yield, suppose if I want cinnamaldehyde to be the better yield, then I want to stop this self condensation to happen. How can we stop that? You take benzaldehyde and OH minus, which is the base we use for the reaction, then add the aldehyde which has alpha hydrogen slowly drop by drop. So as you add drop by drop, then the product which you will have is mainly about the crossed product. So the product which you will have is pH, CHOH, CH2, CHO, which on heating will get cinnamaldehyde. Okay. So this way the yield could be almost 99%. So in case if you want to increase the yield of cross product, especially in Claisen-Schmidt, you can add the alpha hydrogen containing aldehyde or ketone drop by drop. Okay. Most of the time you would be asked what is the cross product in this case. So you can see this HCHO does not have alpha carbon only, so there is no chance of alpha hydrogen there. So in that case, the cross product in this case would be, this group C double bond O. This is the carbon anion which will attack on HCHO. So we will get this becoming CH2OH here. Now if it is given excess, if the number of moles are given more, so which means all the hydrogens which are present here, you have 2 alpha hydrogens here and 2 alpha hydrogens on this side also. So on all the side we can see HCHO again substitute, and we can have this double bond O with OH, OH, OH and OH formation like this. So this will be the final product. So in case of cross product, you just have to be careful what is to be the product seen. Okay. Now the next type of aldol is intramolecular, where within the molecule we have at least two sites of carbonyl positions. Now in these cases it has been seen that only 5-membered ring or 6-membered ring are the more stable forms which are forming. So you need to check out for whether we can get 5-membered ring or 6-membered ring. Now let me show you this. Suppose if at all I expect that carb anion is forming here and it will attack. What is the number of carbon rings here? So you can see 1, 2, 3, 4. So 4-membered ring. So definitely this won't take place. So I'll just delete that. Next, if we see that this molecule here, if it is forming carb anion and if it attacks here, see it is 1, 2, 3, 4, 5, 6. Yes, this can definitely take place. Here it is symmetrical on both the sides. So this carb anion attacking here or this carb anion attacking here or this attacking here, it is the same thing. Okay. Similarly, this carb anion here attacking is same as this carb anion attacking here, which doesn't take place is what we have learned because it is giving 4-membered ring. So the chances of this attacking here would be more, right? So this carb anion will attack here and that would give the product, major product, and you will get this as double bond O. Okay. So I have directly written the condensed product here. So you can see first what is forming in case if you need to be more elaborative on that. So first you can see in this 6-membered ring, so we will have this OH formation here because this double bond O will become OH with a methyl group it is present, and on this position you can see on this position 1, 2, 3, 4, 5, 6 position. So here also if you can go from here 1, 2, 3, 4, 5, 6 position we have connection. So on this 5th position we have this double bond O, right? So after elimination we will get this form. Okay. See the next one also. Just check out which connection is better. Here if you see this side, the only difference between these two is this is a ketone on both the sides. Here it is aldehyde on one side, ketone on the other side. Okay. So there are two chances here. Either this carb anion can attack here or this carb anion can attack here. If this attacks, it will only get 4-membered ring. So this doesn't take place. So if this attacks, you will get 1, 2, 3, 4, 5, 6, 6-membered ring. So the attack would be from this end and you will get the product as similar as what we have learned above. And here we will just have double bond O, C double bond O with conjugated double bond here. Got it? So you got to recognize the places from where the attack would be. Now check this. See the next case here. Now in here the attack would be possible from here to here or it could be possible from here to here. Okay. The same acts from the other side also, here to here or here to here. So I'm not writing that. So if we get to attack from here to this point, so we'll get 1, 2, 3, 4, 5, 6, 7. So I'm getting a 7-membered ring. While here if it attacks 1, 2, 3, 4, 5, 5-membered ring. So as comparatively if you check out stability, this 5-membered ring is more stable as compared to that of 7-membered ring. So that is more favor. Okay. So therefore the product which you need to write would be a 5-membered ring. So like this double bond O, because this entire thing C double bond O methyl that comes on that 5th carbon from where the attack would be, and that is attacking on the 1st carbon which also has a methyl group. Okay, and here there was OH forming which on heating will give the condensed product. The condensed products would be double bond here with this C double bond O. So that will be the final product. Same logic for the next one. Instead of methyl here there is hydrogen. So rest all would be same here. Rest all would be same here, except that there is no methyl group here, there is only hydrogen here. So double bond. That would be the product. Right. See the next case here. In this case, if you check out again, one, if the attack happens from this end to this end, okay, if the attack happens from this end to this end, now we will get 7 membered ring, 1, 2, 3, 4, 5, 6, 7, in fact 8 membered ring. So that is not favorable. But if it attacks from this carbon here, from here, now we can have 1, 2, 3, 4, 5, 6 membered ring. So the attack would be to form the 6 membered ring here with this group lying here and a double bond forming here. So that will be the final product. Now in here, in this case, right, in this case if you check it out, there is an alpha hydrogen here, there is an alpha hydrogen from this end also it could attack this end and this end. So these are all the different alpha positions which you have. Suppose if this attacks here, so we will make this as 1, 2, 3, 4, 5 membered ring here, and rest would be becoming 7 membered ring, and we cannot avoid here for that formation because there is no other way we can get any better ring formation than that. So the attack would be from this methyl, and we will get one 5 membered ring here like this, and attached to that 5 membered ring only we will have one 7 membered ring, double bond O and OH here, which on heating will give us double bond O and double bond here. So that will be the final product. Sometimes the question would start, rather than starting with the aldehydes or keto form, it would start from ozonolysis, right? And this is a previous IIT question where first he wants us to start with the ozonolysis and then do the reaction here with KOH so that aldol can be seen. So on ozonolysis we know that this double bond will break and zinc is given, so it is an reductive ozonolysis. So first we would get CHO on both the sides here. This is what we will get. So within the molecule I have two aldehyde positions. In the presence of KOH I can expect the aldol condensation, intramolecular aldol condensation to take place. So this way, and you can see that suppose if this is C double bond O and H here. So this carb anion can connect onto this carbon, which is C double bond OH. Okay. So now see the ring here, 1, 2, 3, 4, 5. So 5 membered ring is formed here. So 5 membered ring is formed like this with OH forming here, and this carbon already has a CHO on it. This on further heating we will get a double bond formation here. So with CHO. Alright, so that will be the final product. So I hope you understood how the intramolecular aldol works. So always stick to 5 membered and 6 membered rings for the final product. Now within this there is a special case called Robinson's annulation. Robinson's annulation is that first we make a Michael's addition followed by the aldol. Michael's addition is always about 1,4 addition. Okay. For example, if you have this group here, if there is already a conjugated position here, so I'll take this as 1, 2, 3, 4 position. So the addition would be, which means the nucleophile, the incoming nucleophile will attack on 4 and O minus will come, which will attack on the H plus or the electrophile. Okay. So in short, let me show you that. Nucleophile, if it gets connected here and this pi will shift, this pi will shift onto oxygen, which will connected with an electrophile, then we call this as the 1,4 addition or Michael's addition. Got it. So in already when the conjugate is alpha beta unsaturation is present or conjugate double bond is present, then 1,4 addition is more feasible. So you can see here, now we have a double bond at this alpha beta position. So carb anion from here will attack, this pi bond will shift, this pi bond will shift, and that will form O minus there. Got it? And finally we will reach to this molecule. Let me show you the mechanism here. So first OH minus is extracting proton from here, right? And once it extracts the proton, we will have the carb anion formation. Okay, so this carb anion formation is in resonance stabilization with this O minus here, like this. That is attacking on the double bond O here, making a Michael's addition. So which means this double bond will again close, minus charge will close as double bond, the pi will attack here, double bond will shift here, this double bond will become O minus. So we will get this as double bond O connected with, like this, with double bond and O minus. This is what we have seen. On hydrolysis, this O minus will extract the proton from here and becomes that enol form there. So we will get this as double bond O with, right, with OH, and that OH will become this enol. This is an enol form, right? So enol will again get back to form ketone. So I am directly writing the keto form. Now you see that within the molecule I have an intramolecular aldol which can be done. So I will see for the ring size now. If you check out for the ring size, if carb anion which is at alpha position, this can attack, or this carb anion can also attack. So if this attack happens, it is 1, 2, 3, 4, 4-membered ring. So this is not feasible. So we will remove this. And if the attack happens from this end, it will make a 6-membered ring formation. So carb anion will attack from this end, and we would get this as OH with connection here. Okay, I'll write this OH here, it becomes easy. Like this, with OH here, right, and a double bond O here, and on heating we will get this as double bond O here. So that will be the final product, right? So Robinson's annulation is all about, first going through Michael's addition and then making the intramolecular aldol condensation. Okay guys, I hope you understood that. Right. Next, see the type of aldol is Nitro Aldol. See, if you consider CH3C double bond OH with CH3NO2, okay, CH3NO2. Now nitro is a very strongly pulling -I group. On top of that, if it gets carb anion here, so it can also undergo resonance stabilization with this, okay, like this. So this does help to extract the proton easily. In fact, its pK value is much lesser as compared to that of acetaldehyde. So hence, if you see OH minus, on adding OH minus, now the OH minus will extract proton from the alpha position, alpha hydrogen of nitro group. So we will get carb anion from there, and that carb anion which is forming is the one which will attack on aldehydes. Right, so that's how we will get this as PH COH HCH2 NO2. Okay, and here also on heating we can see that double bond formation is observed. because it can undergo resonance stabilization with NO2. So this will be the final product. So this is Nitro Aldol. So Nitro Aldol is all about the carb anion is forming on the nitro group, and that is attacking on the aldehyde. Cyano also in a similar case, nitro and cyano are strongly withdrawing groups here. So same, this CH3 minus will attack here, where this RO minus is taking away this proton from here. So therefore we will get this as pH, CHOH, CH2CN, which on heating will get pH, CH double bond, CH and CN. So these are nitro aldols and cyano aldols. Okay. A similar type of a reaction is observed, okay, which is a name reaction known as the no-vinegar reaction. Well, this actually happens in esters, but since it is a similar kind, we can discuss here itself. See, this is an active methylene group because both sides there are withdrawing groups, COE. So ETO minus will extract the proton from here, generates that carb anion, and that carb anion will attack here. So which is quite similar to that of the above cases, and that brings the product as pH, CHOH and CH with COET and COOET, which on heating we will get this as pH, CH double bond C, COET and COET. So alpha beta unsaturated diesters. So this is called no vinegar reaction. Okay, I guess you guys understood that, right? So the last type of aldol, I'll just finish that and then you can take the notes. Last type of aldol is the retro aldol, which is exactly reverse of the aldol. So which means if you already have an aldol product, condensation product, we can get back to a new type of an aldol for it. For instance, suppose if there is already an alpha beta unsaturated aldol condensation product. Now, on adding dilute OH minus, what we can expect, this OH minus will again attack here, and this pi can shift here as carb anion. So as it shifts the carb anion formation, you can see that double bond O, carb anion here with ET and OH. Can you see it is more like a Michael's addition here now? So OH minus is first attacked here, but we are not continuing till that 1,4. On 4th position I have added carb anion is here. So once you get this carb anion here, this O minus is extracting this proton, and I would get this as double bond O and H here, ET and OH, sorry, ET and OH here. Okay, this is what has been formed. Now this OH minus will extract the proton from here, right, and makes the carb anion formation there. So we will get this as double bond O, H, carb anion O minus and ET. This carb anion will try to close as a double bond, breaking this bond to make a double bond formation here. Correct? So that will try to make the double bond formation here. Now as soon as that double bond formation comes there, right, so this pi will shift here, so we will get O minus, sorry, this bond is broken, so double bond, this H here, right, and I have double bond O and I have a C double bond O and ET. This is what we have. Now this will again with water can take away this H plus, and I am directly writing the steps. See, you can see this is an enol form. That enol will again convert into keto form. In this case we will have this as double bond O, ET, and here also we will have double bond O, CH3. This is what is formed, right? Now from once you get an aldehydes on both the sides here, you can see intramolecular aldol can happen here now, right? And if you check out this ET, I can write this as CH2 and CH3. I can write that as CH2, CH3. So in the presence of OH minus, I can say that this CH2 can attack here because that can give a 5-membered ring. Okay, that is the alpha carbon which can give 5-membered ring. So that 5-membered ring will convert into this. Check that carefully, right? And that will be giving out this double bond. So in short, if you check out, we started from here, this aldol, we converted into this condensation aldol to a new aldol, to a new condensated aldol product. So which means these two will be in equilibrium. From here you will see it can convert into this form, from this point, from this aldol it can convert into this form. Where does it go, you know, which one will be more, that depends upon which is more stable. So you can see this is more stable, so you will see this is the major product, this will be the minor product, but both will exist. This is called the retro aldol. Okay, now should we do all this mechanism all the time? Not needed. We can see the shortcut for it. See how we can make a simple way to understand here. See, wherever we find this double bond CHO, right, one second, we can make this to work very easily using a simple shortcut here. See, if you find a double bond, just make sure on this double bond, break this double bond, okay, and on the CHO side where there is an aldehyde already present, just add 2 hydrogens to that, and where you broke the double bond, add double bond O to that. That's an easy way to understand. Got it? So if you do that, you will be able to get the product very easily. So you see, if I break that here, you can see that as soon as I break here, oh, I have written it already, sorry. You see, this hydrogen will be given to this carbon and this oxygen will be given to this carbon. So you can see this will become CH2. This is the same carbon. This carbon has become CH2 here. And this below carbon has become double bond O. Now you do the intramolecular reaction once again. So from the alpha position, again intramolecular aldol is formed. So this will be the final product. Right, we got the shortcut of how to do the retro. Same way here also you can see that how do we make the retro from here. So double bond is on this side here. On the double bond side, break it, give 2 hydrogens above, 1 oxygen down here. So here again we will have this as double bond O CH3 here with this double bond O and pH here. So from this carbon onwards you can attack onto this carbon here. So you will get this as the product. Okay, same 6
Sir, in mechanism,
yes, beta.
OH minus being strong nucleophile should attack at key carbon, no sir?
At which carbon?
At carbonyl carbon. In reduction
Here?
reactions we discussed, no sir? Yes, NaBH4, LiH4, different reactions.
Right, there is a product which can be further forming, right? Here you cannot see any product forming. OH minus, if it attacks here, this will become O minus, again it will remove that OH minus, okay?
Okay, yes, correct.
Right. So these are the type of retro reactions you will see. Now this was a question asked once where how many of the following compounds will give 2,3 dimethyl cyclopent 2 enol. Okay, 2,3 dimethyl cyclopent 2 enol. So check out what would be the first of all we'll see what is the reactant he is asking for. So it is, let me write cyclopropane, propanone here, right? On the 2-ene we have methyl here and methyl here, right? So the question asked was, we need to get this, how many of these are possible to do that? Got it? So all of this can undergo retro. Got it? Here it is not retro, here it is already open form. So directly you can see whether there is a carb anion which can be attacking here. So which means from this CH2 minus, if it attacks here, so you may possibly see this as the product. So you just have to check with that.